Have you ever just stared at your laptop and wondered what is actually going on inside that thing? Well, today we're going to crack it open. We're going to see how it goes from just a pile of circuits to the amazing tool you use every single day. Let's dive right in.
I mean, it really does feel like a magic box sometimes, right? You type, you click, things just happen. But it's not magic, it's just some really brilliant engineering. So come on, let's look inside that box and see how all the pieces actually work together.
Okay, first up, blueprint versus building. To really get how a computer works, you first have to understand this one key difference, the difference between the grand plan and the thing that's actually built. And this brings us to this core idea. Think of a computer's architecture as the architect's blueprint. It answers the big question, what is this thing supposed to do? Then you have the organization. That's the actual construction work. The how are we going to physically build it to do all that stuff?
So the architecture, that's the high-level design. It's everything a programmer sees and gets to play with. What commands will the computer understand? What kind of data can it work with? It's really the what of what a computer can do.
And this is the how. The organization is how that blueprint gets turned into a real thing you can touch. We're talking about the nuts and bolts here, the specific memory chips they use, the control systems, all the little interfaces connecting everything. It's the physical reality of the machine.
And here's why this is so important. You can have two computers with the exact same architecture. That's why they can both run, say, the same software. But one might be way faster because it has a better, more efficient organization. Maybe it has faster memory or smarter design. The blueprint is the same, but the building is just, a high-tech skyscraper instead of a regular office building.
So, Section 2, Inside the Computer's Mind. Now that we've got the whole blueprint idea down, let's pop the hood and meet the team of components that do all the heavy lifting.
At its core, pretty much every computer you've ever used has a main team of three working together. You've got the central processing unit, or CPU, you've got the memory, and you've got the input/output units, or I/O. These three are the absolute foundation. First up, the CPU. This is the undisputed star of the show. We call it the brain for a very good reason. This is where all the actual thinking happens. It's constantly doing math, comparing things, and most importantly, it's executing the instructions that all your software gives it. So, if the CPU is the brain, then you can think of memory as its workspace, like its desk or a scratch pad. It's where the computer keeps all the data and instructions that the CPU needs, like right now, for whatever task it's working on. And memory comes in two main flavors. There's primary memory, that's your RAM. It's super fast, but it's also temporary. It's that active workspace that gets totally wiped clean every time you shut down. And then there's secondary memory, like your hard drive. It's slower, sure, but it's where you keep all your files and programs for the long haul. And rounding out our team, we have the I/O units. These are basically the computer's senses and its voice. Input devices, like your keyboard and mouse, those are its senses, letting you give it information. And output devices, like your monitor and speakers, that's its voice, letting it communicate the results back to you.
All right, so we've met the brain, the workspace, and the senses. But how in the world do they all talk to each other? Well, they use a kind of internal information superhighway.
And that highway is called the system bus. It's basically a whole network of tiny electronic pathways that physically connect the CPU, the memory, and all the I/O stuff. It lets them all send signals and data back and forth constantly. This thing is the absolute communication backbone of the entire computer.
But this bus isn't just one big road. It's more like a highway with three different lanes, each with a very specific job. You've got the data bus, which is carrying the actual information. Then there's the address bus, which says exactly where that data needs to go, like a street address. And finally, you have the control bus, which carries all the commands and timing signals from the CPU to make sure everything happens in the right order.
Okay, so we know all the parts of the hardware now. But what does it all do? Well, everything your computer does, and I mean everything, just boils down to working through a very long list of very simple instructions. Every single complex thing you do, from playing a game to just watching this, is broken down into millions, sometimes billions, of tiny, simple instructions. Seriously, just think of it as the computer's ultimate, never-ending to-do list. And the CPU just chews through this list at an incredible speed using a simple four-step rhythm. We call it the instruction cycle. It goes like this. First, it fetches the next instruction from memory. Second, it decodes it to figure out what it's being asked to do.
Third, it executes the command. And fourth, it stores the result. Fetch, decode, execute, store. Over and over and over, billions of times every second.
All right, section 5, putting it all together. Let's see how all these pieces, the components, that bus, the instruction cycle, how they all work together in perfect sync. We'll just walk through a really simple example.
Okay, imagine you press the letter H on your keyboard. That's an input, right? The keyboard, which is an I/O unit, instantly turns that physical press into a digital signal. That signal, which now just represents the letter H, gets shot out onto the system bus. It zips along those electronic pathways, and the other parts of the bus make sure it's headed to the right places, namely the CPU and the memory.
The CPU sees this new data arrive, and it kicks right into its cycle. It fetches an instruction from memory that basically says, hey, when you get a signal from the keyboard, display that character. It decodes that instruction, then executes it, processing your H data.
Then, the result, which is a command to display the letter H, is put right back onto the system bus. But this time, it's addressed to the monitor, another I/O unit. The monitor gets the signal, and boom, the letter H pops up on your screen. That whole trip, from your finger to the screen, happens in a mind-bogglingly small fraction of a second.
So just think about that for a second. From your smartphone to the biggest supercomputer on Earth, this basic structure, CPU, memory, I/O, and a bus, it's all fundamentally the same. So, if that architectural blueprint hasn't really changed much, the real question is, how do we keep making them faster, smaller, and more powerful every single year? Well, the answer, as we saw, is all about constantly improving the organization. But that's a story for another time.